As we saw in the last video, there are a huge number of ways in which distributed systems can fail. And it doesn't make sense for us to try and design a system that is resilient to all of the possible failure modes. Instead, what we do is we design systems that are resilient to entire categories of failure, and we pick and choose which categories we want to failure harden our system against. How do you choose what kinds of things you want to build in order to make your system more robust? Well, you measure the importance of each class of failure. And you do that by coming up with your best guess of the frequency of how often you expect each class of failures to occur, and also the impact. How bad is it if that failure occurs and the system doesn't heal itself? Instead, it pages an operator and requires you to come into work and fix the system when it goes down. Ideally, you would be working at a giant company with a huge track record of failures, and you'd be able to look at data and come up with exact numbers for the frequency and the impact of every failure on your system. But we live in the real world where you're probably building something new that didn't already exist, and so you're going to have to come up with your best guess as to what the frequency and impact distributions will be. So that leaves us with the question, how do we divide all of our many failures into categories, and what kinds of things can we do to fix those failures automatically? So the first way I want to divide all of our failures up is into network failures versus node failures. Why are we dividing them in this way? Well, it's convenient because if you go out and you try and hire people to solve these problems, you can hire network engineers and you can hire software engineers, and they often have non-overlapping expertise. It's also convenient because we can go and decide which off-the-shelf solutions to use if they already exist. So let's first start by talking about network failures. Networks fail in a huge number of ways. You can lose packets, you can get corruption, you can have routing issues, you can have multipath issues, you can have congestion collapse. You just go and talk to a networking person and you will be astounded at the many failures they describe, which you just never thought could possibly happen. My personal favorite, which I learned when I went into industry, is backhoe fade. That's what happens when a backhoe cuts your network cable in half. Who knew? Well, apparently it is one of the more common failures that you have to deal with if you're dealing with a distributed system that spans multiple cities or countries. What we really want is we want our networking experts to give us abstractions, give us a library we can use, which will then abstract away all of our network issues and make us have to deal with a simple abstraction. And so the simple abstraction that they provided us with is this. You get a library used for communicating between two processes on two computers, and either your data goes from one computer to another, or it doesn't. That sounds like a simple abstraction. That's what TCP/IP gives you. And it's really easy to use, so why not just use it? And it deals with things like multipath effects and congestion and having to retransmit on lost packets, and it does a little bit of protection against data corruption on the wire. What it doesn't really handle for you is security. You will have to rely on encryption or some form of cryptography if you want to have some security guarantees as well. I'm not going to go into detail about exactly what security you need for your application because I don't know what you're building, but just as an example, SSH will provide an encrypted tunnel with authentication between any two nodes. And many distributed systems rely on SSH to provide a tunnel between all of the nodes which are executing. So what's left? So the networking folks have given you this nice abstraction. They've given you point-to-point links between your nodes, and they can do all sorts of things to harden those links and make them behave in nice, easy to understand ways. But there are two things that they can't really give you. And one is a guarantee that your packets will always get there. Sometimes the network goes down, and your application will have to deal with that. The second thing that they don't give you is they don't give you performance guarantees. Or if they do, they're probably lying. And so this second problem, I'm going to punt on for now. And the reason I'm going to punt on it is if I'm a node and I'm talking over the network to another node somewhere else, and my connection is slow, I can't reasonably tell apart my network connection being slow to the node, or just the node on the far end of my connection is slow. And so I'm going to treat those cases both the same in the distributed systems that I'm designing, unless I have a really good reason to try and tell them apart. I'm going to punt the discussion of what to do about slow nodes to when we talk about node failure as opposed to network failure. So let's talk about loss of connectivity. How does that affect your distributed system design? So consider a distributed system. Here's an example where the circles I've drawn are the nodes and the lines in between them are the network links. I've drawn a generalized distributed system here where every node isn't necessarily connected to every other node. Sometimes to communicate between two nodes, you need to hop from one node to the next and then on to another node until you get to your destination. But in this example I've shown here, it is a connected distributed system. It is a connected network, or in graph terms, it is a connected graph. So every node can communicate with every other node. So this means we can run algorithms that rely on the fact that every node has the ability to communicate with every other one. Great! What happens if one of those nodes goes down? Let's pick this one in the middle. When that node goes away, we've lost connectivity between one subgraph, the 2 nodes in the bottom left, and another subgraph, the 8 nodes in the top right. This is called a network partition. This is bad news for many algorithms we might be running in our distributed system. And it can get even worse if we lose a second node, as I show here. When you lose the second node, instead of being partitioned into 2 subgraphs, it is partitioned into 3 subgraphs. Which, depending on what you're doing, might be a really bad thing. So just to define our terms, a partition is when you have a distributed system and at least 2 components of the system continue to run, but they can't talk to each other. They've lost their ability to communicate. Often a partition is a temporary state until a network failure resolves itself or a node failure resolves itself. But we have to really understand partitions in order to design a robust algorithm that can successfully work and do the right thing. Why do we care about partitions? Well, we tend not to care about it if our distributed system is executing a read-only workload. If we're only serving requests and not actually changing any state in our distributed system, there's very little need for the nodes in our distributed system to communicate with each other. So if they can't communicate with each other, who cares? Most distributed systems aren't like that. Most distributed systems have state, and that state can change. For example, if the system we're working on is a comment system like Facebook, where we have posts and users want to attach comments to them, our users might be talking to different nodes. And if we partition our distributed system into 2 subgraphs, as I've shown before, then the state could diverge. Users talking to one subgraph might add comments to a posting, and then users talking to another subgraph might add comments to the same posting, and they wouldn't be able to see each other or read each other's comments, and so the thread of conversation would diverge. Okay, you can actually deal with that if you write an algorithm, write some code, that when the partition heals itself and you get one system again, you identify these conflicts and you weave the conversation back together. That is called tolerating a inconsistent state, and that can be hard or can be easy depending on your application. And there's actually been a huge amount of academic work put into coming up with different relaxed consistency models that allow you to do that exact operation, which is weaving things back together again when your partition heals. Or if you want to do the simple thing, which, well, simple in some ways, complicated in others, you can just say, I'm going to maintain a strictly consistent system. And in order to do that, what you need to do is you need to figure out when your system has partitioned and make sure that all but one of your subgraphs disables writes to any particular data item when the system is partitioned, so that you don't end up with any data item in an inconsistent state. So, great, we can go with that simple approach, and that will maintain consistency, but it has a cost. And the cost is we will have lower availability than if we allowed for a relaxed consistency model. And what do I mean by this? Well, if, in the example before, one node goes down, we don't lose just one node, we lose 3 nodes, because the other 2 nodes that had to go through that one, at a minimum, have to shut down as well, so that we don't end up in a partitioned state. And there's actually a really deep discussion we could get into about the trade-offs you have in your design here between availability and your consistency. The more consistent you want your system to be, the more it will cost you in terms of availability, because the outage of one node can take down multiple nodes, or outage of one network connection can take down multiple nodes. And if you want to read all about this, you should read papers that refer to Eric Brewer's CAP principle, which is the consistency, availability, partitioning principle, which says basically you can only have 2 out of 3. If you have a system where partitions are possible, you can either have strong consistency or the best in availability, but otherwise you're going to have to make a trade-off between those two if you want some point in the middle. So let's go back to our simple case where we just want to maintain strong consistency. How could we design an algorithm that can actually give us the ability to detect partitions and do the right thing? So going back to our example, what we would say is every node needs to periodically send some message to every other node, whether it's a heartbeat, a ping message, or whether it's I'm already talking to you anyway, so while I'm talking to you, I just want to make sure, are you there? Are you okay? So if every node knows how many nodes are in the system, n, and every node periodically is talking to every other node, it can count the responses it gets back. And if it ever discovers that there are less than n nodes available and reachable from my present node, then I've got a problem. Some nodes are down or some network link is down. And so I just compare that count. And if that count is less than half or equal to half of the total number of nodes in the system, I should switch myself over to read-only mode and stay in this safe state until the network heals itself. So why that magic number? Why n over 2, the floor of n over 2? Why are we using that threshold? And the reason being that if we used any smaller number, then as an individual node talking to the other nodes in my distributed system, I can't tell apart a scenario from when I'm in a partition that's less than half and the rest of the system is down versus I'm in a partition that is less than half the size of my system and the rest of the system is up and has a bigger group of nodes operating in parallel with mine. So this is the algorithm we use. It's called quorum. You make sure that you have a quorum, which is a strict majority of the total number of nodes accessible and that you can talk to. And the only downside to this algorithm, it's simple, it works well. The only downside is that if you partition your network into three subgraphs, as I've shown on the right, none of them will keep on working because none of them can identify themselves as the only subgraph that should keep on working and guarantee that the other ones will shut themselves down. Okay, so that's what we have to worry about from a networking side, which is when links go down, do we lose the ability to communicate between various parts of our distributed system, and how do we react to it? Let's talk about the individual nodes. How can they fail? Well, the simplest failure that a node can have is it can just stop working. And you can write code that can deal with a node stopping working. So what do I mean by stopping? Your software, if it hits a bug and it crashes, that's a fail stop. If you have a power outage, that's a fail stop. If your hardware, if the motherboard cracks in half, your system will fail stop. If you run out of memory or your disk fills up and your operating system kills you off as a result, you fail stop. Fail stop is great because virtually every engineer knows what to do when a system fail stops. You do one of two things. If the computer is still working, which is stopped on, you reboot it or you restart the system and you bring it back up and load the last good version of your data that you were working on. That's called the checkpoint and restart strategy. And it works great if your computer is still working, so it wasn't a hardware failure, and also assuming that you're okay with the amount of time it takes to reboot the computer and restart it. It's got a high latency to it, and during that time you're suffering an outage, which may or may not be acceptable depending on the application you're writing. So what else can we do other than just reboot the darn thing? Well, the other option you have is to fail over to another node. This is what's also called a hot spare. And what you need is you need to make sure that you're periodically saving your state to more than one node, more than one computer other than your own, the one that you're currently running on. And you need to have some mechanism, such as a load balancer, that can make it so that user requests can be redirected to the new node when the node which you're working on fails. So this is replication and failover. It's, I would argue, in many cases, a superior strategy to checkpoint and restart, with the only caveat that it costs more, because you need to allocate more computers and have hot spares which, when there isn't a failure, may be running at less than their peak capacity. Great, so that's a dramatic oversimplification, but node failure is relatively easy to deal with. What's the other category? Fail-stop behavior on a node is relatively easy to deal with. But what's the other class of failure we have to deal with on the node? The other class is called Byzantine failure. And Byzantine failure is everything that could go wrong that doesn't cause your node to stop. Wait, what does that mean? So, for example, if your program is running along and a particle from space happens to hit your memory, and flip a bit, and it corrupts one of the variables which your program is using, your program might start doing the wrong thing. And you haven't detected it, but it's technically a failure. You're running your program, and you go to talk to another node, and it responds with a version of a message from an older version of the software, and you don't know how to deal with it. Well, there might have been some deployment error that caused an older version of the software to get rolled out somewhere, and what are you going to do? If a node starts running a malicious version of the software because a hacker has attacked one of your nodes, or even a rogue employee has deployed bad software on one of your nodes, that is an example of a Byzantine failure. And so, how are you going to design a system that's able to tolerate Byzantine failures? And this is actually a fascinating field of computer science research, and many PhDs have been have been written on trying to figure out how do you write software that keeps on working when even the worst possible thing that could go wrong does go wrong. And in the next video, I'm going to talk about the original paper which launched this whole field and also named Byzantine failure. It's not because we hate Romans, it's because of a cute story about some generals fighting each other, and it's called the Byzantine Generals Problem, is the name of the paper. We're going to talk about that next. But one of the most interesting things that's come out of this field of research, I think, is the impossibility proof, which is you can actually design a system that tolerates one or more Byzantine failures as long as you don't have too many of them. And it's not easy, but you can actually do it. And so that's kind of cool. On the other hand, it is hard to write a system that tolerates Byzantine failure. And you probably don't want to build such a system unless you absolutely have to, because it's really hard and it's not necessarily super fast to design a system that can tolerate this class of failure. So my advice for most system designs is don't try and tolerate Byzantine failure. Instead, identify the failures which occur most frequently and try and transform them into fail-stop instead. So I told you before that a bit flip in memory is an example of a Byzantine failure, because what's your program going to do if its memory's changing out from under it? There are things you can do to stop that from causing you to be totally lost. You can put checksums on all data structures when you store them into memory and verify those checksums every time you read the data structure. If a checksum verification fails, you can just commit suicide, kill the program, let it restart, and let your recovery mechanism deal with the fact that one of your nodes just went down. That might be a little bit extreme if it happens too often. So instead of using checksums, you might want to use more memory and store error-correcting codes instead, so that when you get a checksum validation failure, you can correct the error instead of just aborting and quitting. Or you can use ECC memory, and that will help you somewhat on your machine as well. You can do similar things with other invariant assertions. You just add assertions throughout your code, such that when something goes wrong and looks slightly funky, you just make the program die, restart, and fall back on whatever strategy you've implemented already for dealing with node failure. Great. This actually deals with performance issues as well, to a certain degree. If a node gets stuck in a tight loop doing something it shouldn't do, it will perform very badly. If you have timeouts on every request that you send, when the node gets stuck, all of its requests will get killed, and it may abort, restart, and come back, hopefully in a better state. Now, there is a risk in adopting this fail-stop strategy, and the risk is this. If your nodes hit this kind of error too frequently, or if they hit them in a cascade, you can get a cascading failure across your cluster, which will require operator intervention to recover from. Hope is not a strategy, I've heard people say many, many times, but you could hope that this doesn't happen very often. Or you could try and carefully tune your system so that this doesn't happen as often as you want, as you hope. Well, doesn't happen too often. So, let's summarize all of the classes of failure which hopefully your distributed system can deal with. First off, we divide all of our failures into two categories: network failures and node failures. On the network side of things, you try and use libraries such as SSH or TCP/IP to make it so that you can abstract away the network and treat it as a series of tubes or pipes connecting your various nodes to each other, which packets can either go through or they won't get through, and so your connection either works or it doesn't. Once you then have created fail-stop behavior on the network, you only have to worry about the problem of partitioning of your network, and you need to design your algorithms in order to do something sensible when a partition happens. Then, on the node level, you should divide your failures into fail-stop, and you need to adopt some sort of strategy to recover from that, which is either a checkpoint and restore, or a failover to a replica. And then Byzantine failures, which hopefully don't happen very often, but the ones which do happen often enough for you to care about, you should be working hard to transform those into fail-stop behavior so that you don't have to worry about them anymore. And then, I've sort of shied away from the last category, which is Byzantine failures, which who knows what you can do about them because they're just too crazy and hard. And you may never solve them, depending on the failure class, or you can go on to the next video where I'm going to talk about the Byzantine generals problem, and we can talk more about how this whole class of problems has been attacked by computer scientists.